Okay, we are moving into static electricity part 2. Okay, in this section, we'll be discovering how are objects electrostatically charged. How do we charge a neutral object to become positive or negatively charged? Okay, and this is you can read this yourself about how is lightning being formed. It's basically because of clouds rubbing against each other, and then it results in positive charge, the top parts of the clouds, and negative charge at the bottom part of the clouds. And this negative charge will in turn, okay, repel all the electrons on Earth far away from it, so that the bottom part of the Earth nearer to the clouds is positively charged, and eventually after a long period of time, when the charges build up, when sufficient charges build up, okay, then electricity or electrons will flow down, okay, across these insulating layers of air, okay, and when electrons flow down, you'll form your lightning. Okay, so you can read through yourself. Okay, but before we start on how do we make an object become charged, we need to understand that there is actually two categories of materials. One is called insulator and one is called conductor, and you need to know the difference between them. Okay, for insulators, there are charged particles plus and minus because they are made out of atoms. But then for an insulators, the charged particles cannot move out of the insulator. They can only move slightly within themselves, but not out of the material. Okay, so we say that it doesn't have much ability to conduct electricity. Okay, so examples are like glass, wood, silk, perspex. Perspex is a type of plastic. So the way of getting an insulator to be charged, okay, is by friction. Okay, just by simply rubbing against each other, okay, you can get it charged. But for conductors on the other hand, you also have charged particles, but these charged particles can flow easily. It can flow easily into and out of the material. Okay, that's why they have a high ability to conduct electricity. So for conductors, you cannot charge by friction because in friction, after rubbing, the electron doesn't stay on the material, it moves. So it can easily move from one material to another material. So you can't do friction. So for conductors, in order to get them charged, they can only be charged by induction. So examples of conductors are most of the metals like copper, steel, etc. Okay, most of the metals are electrical conductors. Okay, so you can read this, rubbing a balloon against a hair. Okay, so in this case, we are having two insulators. The balloon, which is rubber, is an insulator, and your hair is also an insulator. Okay, when you rub these two things together, you are actually causing these two items, the balloon and the hair, to be charged. And when two objects are being rubbed together, they actually becomes oppositely charged. So when one is plus and one is minus, based on the law of charges, unlike charges attracts, so that's why when you rub your balloon against your hair, you will see that your hair will get stick to the balloon. Okay, so why do electrons move or charges move when they are being rubbed? Okay, you need to know that in electrostatics, okay, although there is positive charge protons and negative charged electrons, okay, it's always the negative charges that move. The positive charge is stationary inside the nucleus, okay, it's held together in the nucleus with the protons and neutrons are held together there. Okay, they are not free to move out of the atoms. Okay, the only one that is possible to move is always the electrons or the negative charges. So whenever we talk about electrostatics, whereby charges move from one place to another, it's always the negative charge that moves. It cannot be the positive charge that moves. Okay, so how then would I know whether the negative charge moves from one area to another or vice versa? Okay, this depends on the type of material being used. Okay, different materials have different attractions for electrons. some materials will tend to attract the electrons more than others. Okay, so for those materials where I have a stronger attraction of electrons, more electrons will flow to me, and as compared to another material that has less attraction for electrons. So that material that has less attraction will lose the electrons, okay, to the one that has a stronger attractions for electrons. So for example, in the example previously, where you rub a balloon with your hair, okay, both of them are insulators and both of them contains charges. So what happens is the balloon have the rubber in balloon have a stronger attractions for electrons, while the hair have a weaker attraction for electrons. So the less tightly held electrons from the hair will actually be transferred over to the balloon during the rubbing. Okay, so once the hair loses electrons, okay, the electrons gets transferred out, it loses electrons, the hair actually becomes positively charged. But on the other hand, the balloon, which has a stronger attraction of electrons, it will attract all the electrons from the hair, and then it gets transferred to the balloon, and the balloon now have excessive electrons, so the balloon now becomes negatively charged. So with the hair being positive, the electrons, the balloon being negative charged, so they are opposite charge, and based on the law of charges, unlike charges attract, so the hair and the balloon will attract each other. Okay, so you come into this diagram, it shows you the structure of the atoms in hair and balloon, okay, before rubbing. Okay, you can see that I have 4 plus and 4 minus for each atom in the hair, and similarly 4 plus and 4 minus for each atom in the balloon. So we say that the hair and balloon in the original state, they are neutral. Okay, but balloon has a stronger attraction for electrons. So now, after rubbing, during the process of rubbing, okay, some electrons will be rubbed off the hair, and then it goes over to the balloon. So you can see over here, okay, the surface where it's being rubbed over here, the electrons, I have 1 missing electrons. This extra one, this 1 electron has been transferred over to the balloon side. So now I have 4 plus over here and 3 minus. So my hair will become a positively charged surface. Okay, while my balloon side, I will gain an electrons from the hair. So my balloon side have an extra electrons. My balloon on this side of my balloon, it becomes a negatively charged surface. Just take note that they are insulators, so the charges cannot move freely. Okay, once I move, I can't move back unless I rub. But as I rub, more and more electrons get transferred over because balloon have a stronger attractions for electrons. Okay, so I have a positively charged surface here and a negatively charged surface here. Unlike charges attracts, these two surfaces will get attracted to each other. Okay, so I give you more examples over here. Okay, so this is what it mentioned. Hair and balloons are both insulators. The electrons cannot move freely throughout the material. So only by rubbing, electrons get transferred to the balloon surface. And these electrons cannot move elsewhere because balloon is an insulator. Okay, so similarly, the hair is also an insulator, so electrons cannot move around to go back to the hair. So the hair will have vacant electron sites, okay, empty electron sites. So they can be charged by friction, rubbing. Okay, so let's take a look at another example. Okay, you have a glass rod, which is an insulator, and silk, which is also an insulator. You rub them together. Okay, electrons actually move from the glass rod to the silk. Okay, so once electrons move over to the silk when you're rubbing, the glass rod loses electrons. So the glass rod becomes positively charged. On the other hand, the electrons go over to the silk. So the silk gains electron and becomes negatively charged. And this is the diagram. So before I'm charged, I have equal number of plus and minus. I'm neutral, glass rod, neutral silk. After rubbing, electrons gets transferred over to the silk cloth. So now I have lesser electrons on the glass rod. My glass rod becomes positively charged. My silk becomes negatively charged with more electrons, and since they're oppositely charged, they will attract each other. Okay, now you may pause the video now to think of whether these statements are true or false. Okay, I'm going to go through now. It says that a plastic rod is rubbed on a duster and it becomes positively charged. Okay, so the plastic rod becomes positively charged. Okay, so the first one, the rod gains proton. Okay, remember I mentioned that only the electrons move. The proton stays inside the nucleus. It doesn't move. So the rod becomes positively charged not because it gains protons, but it's because it loses electrons. So the first one, the answer is false. For the second one, the duster gains electrons. The answer is true because the plastic rod becomes positively charged because it loses electrons. So where does the electrons go? If the plastic rod is rubbed with a duster, so the electrons go over to the duster. So it's true. The duster gains electron. Okay, so the duster lost electrons must be false. So now the duster has gained electrons. Okay, now I have more electrons. So I will have becomes negatively charged, not positively charged. So it's false. Okay, and then the rod, on the other hand, yes, it becomes positively charged because it has lost electrons. It's true. And the duster is positively charged, not negatively charged. Okay, so sorry, the duster gains the electron, so the duster has becomes negatively charged. So it's true. Okay, that is for insulators. I charge by rubbing. So as I rub, electrons gets transferred from one material to another. So one material becomes positive, one material becomes negatively charged, and then they attract each other because of unlike charges attracts. Okay, in this second part of charging materials, we are going to talk about charging by induction, which is for conductors. Okay, so conductors cannot be charged by friction. They can only be charged by induction because the electrons can be easily transferred in and out of the material. It can be easily transferred to and away from the conductor, unlike insulators. Insulators, once I transfer, I stay on my material. So my material, one side will be positive charge, one side will be negative charge. But for conductors, because the electrons can easily flow around, the charges don't stay on it. Okay, so you cannot do by friction, you do by induction. So what exactly is induction? Induction involves placing a charged object or a charged rod close to any conductors, but not touching it. The process of induction is always just bring close to it, but not touching it. Okay, and this, whenever you bring a charged object near to a conductor, it results in redistribution of charges in the conductors, because in conductors, the charges can move around easily. So what do I mean by that? Let's take a look at this. The first one, we go into charging by induction for two conductors. Okay, so I have two spheres. They are made of metal, so they are conducting spheres, meaning they are conductors. Okay, they are placed on insulating stands so that the charges will not be able to flow down to the ground. Okay, just take note, charges likes to flow down to the ground. So because they are conductors, the charges can easily move out of them. So I do not want the charges to move out of them to the ground. So I put them on insulators or insulating stand. Okay, and these two spheres are touching each other, so the charges can move easily within these two spheres. Okay, and remember, again, it's the negative charges that move, not the positive charge. Okay, so over here, I'm going to use induction. Induction is a process whereby I place a charged object very close to it, but not touching it. So over here, I place a positively charged rod close to these two neutral sphere. Why is it neutral? I have equal number of minus an equal number of plus. So it's a neutral sphere. So once I put the positive charge here, okay, it will result in redistribution of the charges in the two spheres. Okay, because of the law of charges, as I bring the positive charge rod near to it, all the electrons in the left-hand side and the right-hand side, all of them will move towards the left-hand side, closer to the positive charge rod. Okay, because unlike charges attracts. So all the negative charge will be moved to here. So this side of the sphere will become more negatively charged, while the right side of the sphere will have lesser electrons, so it will become positively charged. We say that the left side is induced with a negative charge, the word induce, okay, because it comes about from the positive charge rod that is placed close to it. So we say negative charge are induced on the left-hand side and positive charge are induced on the right-hand side, or the right-hand side becomes positively charged. Okay, next. Okay, I want to get these two spheres to be charged up. Originally, they are neutral. So now with a positive rod nearby, the charges have already redistributed. So now what I need to do is I just need to separate these two conducting spheres. Once I separate, the charges cannot move back to, like the negative charges cannot move back to the right-hand side sphere because they are not in contact with each other. Okay, so it cannot move back. So the purpose of separating them is to keep the charges intact on each of the sphere. So I have the left-hand side negative charge, the right-hand side positively charged. The last step, okay, is I'm going to remove this positively charged rod. Okay, so once I remove, my negative charge won't stay at this right-hand side. My negative charge will be redistributed across this whole entire sphere. It will spread out. Okay, so the negative charge becomes like that, and the positive charge will also spread out. Okay, so now you have two spheres that have equal but opposite charges. Okay, so you have the left-hand side becomes negatively charged, right-hand side becomes positively charged. That is how we charge two conductors. Okay, the next one, we go into charging one conductor. So if I only have one material that I want to charge, so the same thing we do by charging by induction. The same thing now, we'll do an example with a negatively charged rod. So I bring a negative charged rod close to a conducting sphere, again placed on an insulating stand. Again, this negative charged rod will redistribute the electrons inside this conducting sphere. So negative charge will repel all the electrons to the right-hand side. So all the electrons will come towards this side, and then I will leave the left-hand side with lesser electrons, so the left-hand side will become positively charged, while the right-hand side will become negatively charged. Take note that this conducting sphere is still neutral at this moment because I have equal number of plus and minus. But I want to make it charged, become charged. So the next step is what we call earthing. Okay, I'm going to earth the conductor. What do I mean by earth? It simply means I provide a path to the ground. Okay, in physics, earth means ground. Okay, or we call it grounding. Okay, so your body is a good conductor. Charges can flow through your body. So the easiest way is to touch the conductor. Okay, so if I were to touch the conductor, okay, the electrons will be repelled away. Okay, because of this negatively charged rod. I don't like my electrons in this conductor. Okay, it will repel away. So the electrons will actually flow down. Okay, so when I lose all my electrons, I will be left with only positive charge. Okay, I cannot remove this rod while I'm touching the sphere, because if once I remove this rod, okay, the electrons will not be repelled and my positive charge will not stay here. So in order for my charges to stay and my electrons to be repelled away, my negative charge rod must be still in place while I touch the sphere. Okay, then after that, I remove my hand, okay, because all the extra electrons has already been repelled down to the ground. Okay, so I'm only left with lesser electrons now. So my entire sphere will be positively charged. But I don't want my sphere to be like that. So the last step, then we remove the negative charge rod so that I will redistribute out the positive charge. Okay, so now I have a sphere that is positively charged. If I want a sphere that is negatively charged, then simple, I just take a positive charge rod over here. Okay, then I will attract all my electrons to this side, and then I will also, once I touch it, I will attract more electrons to flow up. So I will end up with a negatively charged sphere. Okay, so let's go in depth into what is the process of earthing. Okay, instead of touching the sphere, we can actually just connect one end of the sphere to a metal wire or any conductors. Okay, so as long as I provide a path down to the ground, that process is called earthing. And that path must be a conducting path. So the most common one is just to attach any metal wires to it. Okay, so the definition of earthing you need to know. Earthing is a process which neutralizes a charged conductor by providing a path for the excess electrons to either flow away or flow to the conductor. Okay, it depends on whether the conductor, over here the white sphere, whether the conductor is positively charged or negatively charged. The main purpose of earthing, the main purpose of connecting to the ground is to neutralize any objects. Okay, so if you take a look at this picture, you count, I only have 4 plus, but I have a lot of minus. So this is actually a negatively charged sphere. Okay, so now I am going to earth it. Okay, means I'm going to connect a wire to it and touching the ground. So the moment I earth it, earthing is a process to neutralize it. So now I don't want so many negative charge because I have too much negative charge. So what happens is I don't want so many electrons. So all the negative charge will now go down. The extra ones will go down. Okay, so when the extra one goes down, I don't have so many negative charge. I have equal number of plus and minus. I will lose electrons and I will become neutral. Okay, but on the other hand, you look at this right-hand side white sphere. There is more positive than negative. So this is actually a positively charged sphere. So what happens when I do earthing? I'm going to neutralize it. How do I neutralize it? Remember, the positive charge cannot move. So I cannot have positive charge moving down to the ground. Instead, electrons is the one that move. So I have not enough electrons here. Electrons will move up. Okay, these 3 electrons will move up into this sphere until I have equal number of plus and minus. So the positive charge sphere actually gains electrons from the earth and becomes neutral. So the earth or the ground is actually a huge reservoir of electrons. It has many electrons. Electrons can go down, electrons can come out. Okay, can come out. So this entire process of neutralizing it is called earthing. Okay, so can you test yourself? In the following case, can you draw the direction of electron flow? How do we represent earthing? We represent it by this symbol. Okay, this is a wire, and this symbol where I have lines getting shorter and shorter, minimum 3 lines. Okay, I don't need so many lines. Usually we just draw 3 lines, one long, the longest, then long and shortest. Okay, 3 lines to represent earthing. This is connected to the ground. Okay, so in the first case, I have a negative charge rod, a negative charge sphere. So I have too much electrons. So electrons should be flowing downwards. Okay, in the second case, I have a positive charge sphere. So in order to neutralize it, I need electrons. I need electrons to flow up to it. So electrons will be moving up in this case. Okay, next. Okay, so we have looked at how insulators are being charged and how conductors are being charged. Okay, so now we take a look at what happens when a charged object is placed near to a neutral object, what happens to the charges inside it? Okay, you can scan the QR code, okay, and then you can see what happened. I'm going to illustrate over here. Okay, if you scan the QR code, you should be able to see this. So over here, I have an object over here is neutral. You can't see that the positive charge, all you can see is negative charge because the positive charge is behind the negative charge. Okay, so now I'm going to add in a glass rod that has been wrapped. Okay, so this glass rod is positively charged. Okay, so what happens is this round can over here is neutral. I have equal number of plus and minus. You can see that the plus will remain at its original position. But once I bring a positive charge rod nearby, what is going to happen is, unlike charges attract, so all the electrons here, electrons is the one that can move, will be attracted towards the side that is nearer to the positive charge rod. But the electrons cannot move out of it because this is an insulator. So my electrons cannot move, although I would like to move because I'm attracted to the plus, but I cannot move. Okay, so all the electrons will be transferred over here. So you see, if I were to shift my positive rod over here, can you see all the electrons will be again attracted to this side? Okay, so I will leave this side of my can a little bit more negatively charged. Okay, but the entire can is still neutral. Okay, but this side will be slightly more negatively charged. Okay, so it will get attracted. So a charged object will always attract a neutral object. Okay, it works for in the other way. So now I remove it, all the electrons go back to its original position. Now I introduce a rubber rod. Okay, a rubber rod is negatively charged. So once I bring the negative charge rod nearby, you can see that all the electrons inside will get repelled to the other end, but it cannot move out, okay, because it's again an insulator. So it stays there, but it's mostly repelled to the other side. So we will leave this side, which is nearer to the rod, positive, and it will attract. So you can see, if I bring it over here, the same things will happen. The electrons will all be repelled to the other end, so leaving this side positively charged, and unlike charges attracts, it will attract again. Okay, okay, then next. Okay, so we can see that whenever a charged object is brought near to a neutral object, it will attract. Okay, in the next one, you can scan the following QR code. It will bring you to another simulation that shows you about the balloon and the sweater. Okay, so I'm going to share with you the balloon and the sweater as well. Okay, so if you go into the simulation, we will see this. I have a sweater. Is neutral, there's equal number of plus and minus, and a balloon, which is also neutral, with equal number of plus and minus. Okay, so now sweater and balloon are insulators. I'm going to charge them out. Okay, if you remember, insulators can be charged by rubbing friction. So I'm going to rub the balloon together with the sweater. So you observe what happens as okay, if you can see as I rub, the balloon has a greater attractions for electrons. So electrons actually transfer from the sweater over to the balloon. So the balloon now have more electrons, which cannot move out of it because balloon is an insulator. Okay, so balloon now has more electrons, it becomes negatively charged, while the sweater loses electrons and the sweater becomes positively charged. So if I were to release this balloon now, what's going to happen? Okay, you will see that the balloon will get attracted to the sweater because they have unlike charges now. Okay, so now if I were to bring this balloon close to the wall, okay, the wall is over here. Okay, the wall again is a neutral object. There's equal number of plus and minus, and again the wall is an insulator. Okay, so once I bring this balloon, which is negatively charged, close to the wall, okay, I will tend to repel the electrons in the wall. So you can take a look. Can you see that the electron shifted slightly, but it can't move out of the wall, but it shifted slightly, the electron shifted. Okay, so I leave the side closer to the balloon with a positive charge. Okay, so it gets attracted. The balloon will also get attracted to a neutral wall. So the balloon is now charged. A charged object will attract a neutral object as well. Okay, okay, let's go back to our slides. Okay, so for the previous two examples is when I bring a charged object near to a neutral object that is an insulator. The charges cannot move inside the insulator. Cannot move out of the insulator. Okay, we have another example. What happens when you have a charged object near to a neutral conductor? In this case, it's slightly different because the charges can move out of the conductor. Okay, so the first part, you can take a look at this. I bring a positive charge rod near to a neutral object. Okay, a neutral conductor. So neutral conductor, initially I have equal number of plus and minus, but because of induction, I bring this positive rod nearby. I will result in redistribution over here such that all the electrons in the conductor will move closer to the side of the positive rod. Okay, we say that the negative charges are induced on the left-hand side of the rod. Okay, and then because of unlike charges, there's unlike charges here. This side is slightly more negatively charged. Okay, because of these unlike charges, they will attract each other. So the charged object will again attract the neutral objects. Okay, but the difference is once I touch each other during the attraction, this is a conductor. It's different from just now. Just now examples are all insulators. For conductors, the charges can move easily out of the material. So once I touch, okay, electrons will flow out because electrons will want to move towards the positively charged rod because of the attractive force. Okay, so electrons will be transferred out of the rod, okay, will be transferred to the rod when it touches it. Okay, but this is highly positive. Okay, even with a few electrons being transferred, it is still positive. You can count, I have 1, 2, 3, 4, 5. I have 5 plus, and only 3 electrons get transferred to it. We assume that this is highly positively charged. Okay, so with a few electrons being transferred out, okay, the rod is still positive charge, but it's just less positive charge now. There's still more plus than minus. Okay, but the metal bar, on the other hand, it loses electrons. Electrons actually move out of it. So now I'm no longer neutral. This metal bar now have a positive charge. So once electrons transfer, the neutral object becomes positively charged as well. It has the same charge as the rod. The rod is positive, the metal bar is positive as well. So now, since they have the same charge based on the law of charges, like charges repel, they will actually repel away from each other. Okay, let's take a look at this example. Okay, it says that a charged rod attracts paper bits when it's brought near to it. Explain how an uncharged paper bit gets attracted to the glass rod. So this is a case about a charged object near a neutral object, which is the paper, and why it gets attracted. We have learned that charged object near neutral object, it will always attract. Okay, so the explanation is as follows. You bring a positive charge rod nearby, it will induce, okay, negative charges at the upper part of the paper nearer to the rod, and it will induce positive charge at the bottom parts. Because unlike, so it looks like this, okay? When we enlarge it, because it's positive charge rod, it will attract all the electrons upwards. So the top part will become negatively charged, the bottom part will become positively charged, but the entire paper will still be neutral. Okay, so because the negative charge are nearer to the positive rod, so the attractive force is actually greater than the repulsion force. There will be a repulsion force because plus and plus. Okay, but because the minus is nearer to it, the attractive force is stronger than the repulsive force. So the paper will get attracted to it. Even after attraction, it will not fall off because paper is insulated. The electrons doesn't get moved over to the charge rod. So the paper still remains neutral and will still remains attracted to the positively charged rod. Okay. Okay, next we have something called a gold leaf electroscope. Okay, what is its purpose? It's mainly used to detect charges. So how does a gold leaf electroscope works? Okay, you have a metal piece over here. We call it the metal disc, and then it's attached all the way to the bottom. So this entire thing is metal part. Okay, the disc and all the way to the bottom. Okay, the rod. And at the bottom part, there is actually another metal piece, okay, attached to it, to another separate layer. Usually it's called gold leaf because it's made of gold, okay, but you don't really need gold. You can just make use of any lightweight metal piece like aluminum foil, which is also a conductor. So this entire section is a conductor. The charges can move easily within this entire piece and the golden leaf. Okay, so what happens if I bring an object that is charged? Okay, the main purpose is to detect charge. So in this case, the diagram shows a positive charge rod brought near to it. So if I bring a positive charge rod near to it, okay, this entire thing is conductor. It has plus and minus and is neutral. Okay, all the electrons at the bottom part here, the leaf and the rod, all the electrons will move up. It will get attracted to this positive charge rod. So the top part of this plate will be negatively charged, while the bottom part will be positively charged. And since the bottom part is positively charged, the rod and the leaf are both positively charged. They will repel each other. So you will see that the leaf will fly up. Okay, it will flap up. There will be a repulsion force that causes this leaf to move up. Okay, so once you see that the leaf move up, this thing must be charged. Okay, it works the same way for negative charge. Okay, so if I bring a negative charge rod here, okay, then all the electrons will be repelled downwards. Okay, so at the bottom part, it will be all negatively charged. And since again, they are all light charges, the gold leaf will repel away from the rod. So you will still see the gold leaf flying up. So that's how we detect charges. Okay, but there's a few interesting experiments on electroscope. You can watch the following YouTube link to learn more about electroscope. Okay, next we also have something called a Van de Graaff generator. This Van de Graaff generator is mainly used to generate charges by the rubber belt moving, and then the charges are stored in this metal dome. Okay, so you can watch the following YouTube videos to learn more about Van de Graaff machine. Okay, next, okay, we will talk about how this pine plates works on Van de Graaff generator. Okay, so I'm going to show you the video. Okay, and then you think what kind of outcome do you expect?
This is a Van de Graaff generator. It is used to generate and store charges. Large electrostatic charges can be produced using a Van de Graaff generator. Charges from the high voltage supply are carried by the conveyor belt and stored on the semi-circular metal dome. Here we have some pie plates placed on the dome of the uncharged Van de Graaff generator. In addition, I have an earth sphere placed nearby to the generator. Predict what will happen to the pie plates when the generator is charged up. Here are 4 possible outcomes. Which outcome do you expect and why? Let's observe the pie plates as I charge up the Van de Graaff generator. Notice that the pie plates fly off in the direction of the nearby Earth sphere. When the dome is charged negatively, the negative charge of the dome repels the electrons of the Earth's sphere, causing the side of the sphere nearest to the dome to become positively charged. This creates an electric field between the charged dome and the Earth's sphere. At the same time, the plates gain negative charges through their contact with the dome. The electrostatic forces of repulsion between the pi plates and the dome explains why the pi plate fly off towards the positively charged side of the Earth's sphere.
Okay, so I hope you understand what it means. Okay, so this entire dome is negatively charged, and because it's in contact with this pi plates, this pi plate is a conductor, so the charges move on to the conductor. So all of them will become negatively charged and they will repel each other. So you'll see the pi plates start flying off because they're repelling each other. And because this side is a Earth sphere, okay, this is negative charge and this part will become positive charge because it's near to this negative plate, so you will repel all the electrons down. So this sphere becomes positively charged. So a negative plate, positive charge, there will be an attractive force, unlike charges attract. So the pi plates actually move towards this Earth sphere. Okay. Okay, so next, critical thinking questions. If a charged object X is brought near to another object Y, and there is attraction, can we conclude that Y is also charged? Okay, recap a little bit. In the previous few examples, simulations that I show you, as long as a charged object is brought near to a neutral object, it will always attract the neutral object. So the answer is no. We cannot conclude that the object is charged. Okay, it will attract if they are unlike charges, but it can also attract if the object is neutral. A charged object will always attract a neutral object. So we cannot use attraction to conclude whether an object is charged. To conclude if an object is charged, there must be repulsion because only like charges repel. Okay. Okay, that's the end. You may scan the QR code to test yourself more in depth.